You have a table in front of you with more columns than you can hold in your head, and something in it matters to you. 214 columns, and the thing you need is hiding in the way a handful of them move together. So what do? You start deleting columns to make the problem tractable, your accuracy drops by 4%, and you have no idea which deletion cost you that, and nobody tells you which column mattered. That is a wasted week of your life, and I have wasted a few of them myself. Your trouble is not that you have too much data. 214 columns are cheap to store and cheap to read. Your trouble is that most of them are saying the same thing twice in slightly different accents, and which ones are the echoes? Height in centimeters and height in inches are two of your columns carrying one fact. Your model has no idea, so it will spend capacity learning both. Your distance calculations will count that one fact twice, and every plot you draw is a flat shadow of something you never get to see whole. So how much of your table is genuinely distinct? Hold that question, since a real number is available to you by the end of this, and it is cheap. You would think that throwing away half your columns costs you half your information. It is nothing of the kind, and the gap between those two expectations is where all your value sits. Guessing at that gap costs you weeks of work. Measuring it costs you 4 lines and a coffee, and nobody tells you that either. Note, your frustration here is 120 years old, so you are in good company. Carl Pearson asked this same question in 1901, and Harold Hotelling asked it again with better arithmetic 32 years later. Both of them were stuck where you are stuck. If a cloud of points really lives on a line or a plane inside a much bigger space, can you find that line from the points alone, with nobody telling you what to look for? Principal component analysis is the answer they arrived at, and PCA is the shorthand you meet in every library. 3 moves is the whole of it. Slide your cloud of points until its center sits at the origin. Score every possible direction by how spread out your data looks along it. Keep the highest scoring directions and discard the rest. The eigenvectors everybody talks about, which means the directions a matrix leaves pointing exactly where they were, are not a fourth idea bolted onto that list. They are what the second move turns into once you write it down honestly. What is a direction, arithmetically? Nothing more than a list of weights of length 1 weight per column. 214 columns means 214 weights, each squared in sum to exactly 1. To project a row onto that direction, you multiply every column value by its matching weight and add up the results, which gives you a single number, where that row falls along the direction. Do it for every row and you have the shadow of your whole cloud cast onto one line. So what makes a direction interesting? The score for a direction is the variance of those shadows, which means the average of their squared distances from 0. Large variance means your points spread far apart along that direction, so the direction is telling you something. Variance near 0 means every row projects to nearly the same place, so the direction carries nothing at all. That is the entire definition of interesting here, and it is a wonderfully cheap definition. Spread is information. The covariance matrix is a small idea wearing a forbidding name. Entry row 3, column 9 is the average of your third column times your ninth column across all centered rows. Positive means the two rise together. Negative means one rises as the other falls. Near 0 means they are unrelated. And it is symmetric, since the third times the ninth is the ninth times the third, which is the quiet fact that pays for everything else in this episode. Now the word people use without ever unpacking it. What does an eigenvector actually mean? A matrix takes vectors and returns vectors, and in general it does two things to them at once: it turns them, and it changes their length. An eigenvector is a direction where the turning is simply absent. Feed one in, and what comes back points exactly the same way, only longer or shorter. The factor it's stretched by is the eigenvalue. No rotation, pure stretch, and the stretch has a size. That is the entire content of both words, and I find the plainness of it delightful. Most explanations stop at the recipe, which is the reason all of this feels like magic when it is nothing of the kind. My first instinct, years ago, was that finding the best direction must need a search, 214 weights, a continuous space of directions, some optimizer grinding away for an hour. But hang on. Squared shadows added over rows form a quadratic form, and a quadratic form in many variables collapses into exactly one object, because that object is the covariance matrix you already have. So what does symmetry buy you? For a symmetric matrix, the eigenvectors come out at right angles to one another, and the eigenvector with the largest eigenvalue is exactly the direction of maximum variance. So your search never happens. Your best direction is read straight off the covariance matrix, and the eigenvalue attached to it is not merely proportional to the variance along that direction. It is that variance, in your units, ready to add up. First the algebra hands you a finite sorted list, and then you choose how much of it to keep. Work the smallest case out loud, because the arithmetic is the whole point and you can check it on paper. Take 4 centered rows in 2 columns, 2 and 2, then -2 and -2, then 1 and 1, then -1 and -1. Score the diagonal direction whose 2 weights are each about 0.7. Your shadows come out near 2.8, -2.8, 1.4, and -1.4, so the average squared shadow is roughly 5. Now score the perpendicular diagonal. Every shadow is 0, so that variance is 0. Note, centering comes first, and skipping it is the failure I meet most often. If you do not subtract each column's mean, your leading direction points at where your cloud sits rather than at how it varies. On a set of face photographs, that means your first component is roughly the average face, and it explains a huge fraction of the variance while saying nothing about how faces differ. One subtraction you skipped, and then the whole method quietly changes meaning. Case in point, eigenfaces, the 1991 result from Matthew Turk and Alex Pentland, because that paper is why every computer vision student since has met this idea. Photographs at 92 by 112 pixels give 10,304 numbers per image, so the cloud lives in 10,304 dimensions, and a lab has maybe 400 photographs. 10,000 dimensions, 400 points. Does that sound like it should work at all? It worked, and it still delights me. Around 40 directions rebuilt those faces well enough to recognize people, and the first 20 carried most of it. 10,304 numbers per face, compressed to 40, with identity surviving the trip. Drawn back out as pictures, the eigenfaces directions look like ghostly faces, which is where the name came from. Some encode lighting arriving from the left, and some encode whether the mouth is open. Who designed those axes? Nobody did, because they fell out of the covariance matrix of 400 photographs. Then comes the bookkeeping that makes your decision possible, which is your eigenvalues sorted from largest to smallest. Because the eigenvectors sit at right angles, their variances never double count each other, so they simply add. Divide each eigenvalue by the sum of all of them and you have the fraction of total variance that direction explains. Accumulate them in order and you get a curve that climbs steeply and then flattens out. Before I tell you what that buys you, guess. For a table of 60,000 rows and 214 columns, how many directions would you need to keep to rebuild the whole thing to within 2%? Work it out from what you have so far, and then hold your number for a few paragraphs. Is it closer to 100, or closer to 10? Note, that flattening point has a name, the knee of the screeplot, and choosing it is folklore rather than theory. Practitioners take 95% of the variance, or 99, or wherever the curve stops being interesting to them. No theorem hands you the number, because none exists. We choose it by looking at a picture, which is fine so long as you say so out loud rather than dressing it up in grand vocabulary as a principled criterion. Then comes the arithmetic that should drive your choice, because your reconstruction error is the sum of the eigenvalues you threw away. When that tail is long and flat, doubling the number of components you keep never halves your error, it shaves a sliver off it. On the eigenfaces data, going from 20 components to 40 cut the error by roughly a third, and going from 40 to 80 cut it by less than a tenth. 4 times the storage for 1/10 of the improvement. Quick win, nobody computes the covariance matrix and then factors it, and if you write that in production a reviewer will politely fix it for you. 10,000 dimensions squared is 100 million entries you never needed. Libraries build the singular value decomposition, or SVD, straight from your centered data, because that is what NumberPy calls underneath, what LPAC executes, and what scikit-learn wraps when you type the 4 lines everybody types. Same answer, better conditioning, far less memory. How would you know any of this is true rather than taking my word for it? Test it yourself in about 10 minutes. Center a table you already have, keep the top 5 components, then rebuild it and measure the error. Then keep 5 directions chosen at random instead, and measure again. The random 5 will be dramatically worse, and the size of that gap is the value of the method, in your data, in your units, with no argument from me required. So what did your guess cost you? On tables of that shape it is common to find 50 components holding 95% of the variance, and not at all rare to find 8 holding 90. On NIST, the 784 pixel columns of handwritten digits, around 150 components hold about 95%. And the speed matters more than the storage, because distance calculations that ran across 214 columns now run across 8, so a nearest neighbor search that took 40 seconds finishes in under 2. Now the ways this will fail you, starting with the cost nobody puts on the slide. Your components are blends. Component 1 does not have a name you can say to a colleague, since it is a weighted mixture of all 214 of your columns with signs running both ways. If your deliverable is a sentence a regulator can read, a direction meaning 0.3 times income, minus 0.1 times tenure, plus 212 further terms, will not help you at all. Worse, the method does not know what you are trying to predict, since it maximizes variance rather than usefulness. Ronald Fisher's linear discriminant analysis, from 1936, asks a genuinely different question: which direction separates the classes? Those two answers can come out perpendicular to each other, which is a wonderfully perverse fact. The direction your data varies along most can be precisely the direction that says nothing about your outcome, so people cheerfully drop the one component that mattered while keeping 95% of the variance and feeling responsible about it. Caveat: it also cannot see what your units are. Variance depends on scale, so a column in meters beside a column in millimeters gives the millimeter column a variance a million times larger, and it will own your leading component no matter how unimportant it is. A dashboard table holding dollars, seconds, and click counts together is the trap. Your reviewer then asks the reasonable thing: if standardizing changes the answer, which answer is the right one? Both are 4 different questions. In practice, you standardize unless your columns genuinely share units, as pixel intensities do. It also cannot bend. Every component is a flat direction through your cloud, so what happens when your data curls? No plane will follow it. Points sitting near each other on a curved surface can land far apart in your projection, and you will read that as structure. This is where TSNE and UMAP earn their keep for looking, and autoencoders earn theirs for compressing, since all three are allowed to curve. The trade-off is real, though. TSNE distorts distances deliberately and will happily show you tight clusters that do not exist. And on a table of 12 columns, this may not be worth the trouble at all. The method pays when your redundancy is high and your dimensions are many, so on a spreadsheet of 12 carefully chosen features you will spend interpretability you cannot afford to save arithmetic that was never expensive. Ask yourself which of those two you are actually short of before you reach for any of this. So, back to the question we opened with: how much of your table is genuinely distinct? You now have a number instead of a feeling, and the number is a list of eigenvalues you can compute this afternoon. That is the whole gift, and it does not lie in the compression or in the pretty plot. It lies in redundancy becoming a measurable quantity with units attached, which is something you cannot get from intuition no matter how experienced you are. What eigenvectors actually mean turns out to be far smaller than the vocabulary around them suggests. They are the directions a matrix does not turn. That is all there is in the word. They show up whenever anybody reduces dimensions, since variance in every direction collapses into one symmetric matrix, and a symmetric matrix has directions it only stretches. I still think that is the most satisfying trait in applied linear algebra. 2 things worth your time before your next model. Compute the explained variance curve for the table you use every day, and find out whether it flattens at 5 components or at 90, since that number tells you how much of your feature engineering has been duplicated work all along. Then ask yourself whether the direction you dropped was the one carrying your label. Train once on the components, once on the raw columns, and let the gap answer you. The real question is not whether this compresses your table. It is whether you can afford what it quietly throws away, and that is your call, not the library's.